Hello and welcome. My name is Jan Sorige and I am the WAI International President for 2020. This year, of all years in recent memory, it's a time when WAI Association tradition means more than ever because they remind us to pause and take comfort in the familiar, and that is what we intend to do today. Although we are meeting in virtual, you will recognize there's 3 times honored segments, beginning with a brief annual meeting, followed by the Clockwinding Ceremony, and conclusion with the Mordica Lecture. Together, we will learn new ways to connect and stay close, even if we find ourselves at a distance. And while we are missing seeing each other in person, I want to thank you for joining us today for this virtual gathering. I can see that we have more than 25 members attending, so we are satisfying by the bylaws. With that, I would like to call the WAI Association International Annual Meeting to orders. The minutes have been distributed to you. If there are any corrections, please communicate them through the Zoom chat system now. There are no corrections being offered. The minutes are approved and the distribution via unanimous consent. This year marks the association's 90th years, and what a year it has been. Thankfully, we have had cause to celebrate. With the help of our active members and volunteers, WAI's educational mission has been at full speed ahead. At the beginning of the summer, we added several free webinars and a new live streamcast to keep our global community informed. Then in mid-September, we moved the popular Fundamental of Wire Manufacturing course to a virtual format, which was presented over 7 consecutive Wednesdays. Participation was excellent, as was the give and take during the question and answer segments. Now let us recognize the WAI Association Award winners for 2020. WAI's highest honors are the Donatella Memorial Award. This is given to honor an individual voluntarily contributing to the association. This year, the awards goes to Mr. Andy Talbot of Mid-South Wire Company. Next is the Mordica Memorial Award, which is given to an individual who has made contributions to the wire industry based through research, development, innovation, or other technical pursuit. This award, the year's award, goes to Dr. Gil Baker of Confident Instrument Inc. And finally, the WAI Association President's Award. It's given in recognition of a special service to the association, and Mr. Richard Baker of Brisbane received that honor. Let the records for this meeting show those 3 distinguished award winners for 2020. WAI's Executive Committee, Board of Directors, volunteers, and staff are exploring solutions for events in the years ahead, so we can get back to the business of making wire and cable. With that said, let's set the time. It's just after 10 o'clock in the morning here. Wherever you are, we will take a few moments together to honor WAI's traditional clockwinding ceremony. Whether you have only read about the clockwinding event, seen the celebration on video, or had the occasion to witness the festivity in person, this year will be an unexpected step for all of us as history meets modern day's technology. We are filming from Wire Association headquarters in Madison, Connecticut, where the clock is prominently displayed. Before we are introducing our Clockwinder, I would like to introduce WAI's past president, Ron Reed, who is at headquarters standing by the clock. Ron?
Thank you, Jan. Hello, everyone. Happy Veterans Day. 12 years ago, I had the honor to officiate at the Clockwinding Ceremony during my term as WAI President, and I have returned most years since to share in this custom. There is a rich history and symbolism connected to this stately mahogany timepiece. It was made in London in about 1770. WAI's clockwinding tradition originated when John Rigby and Sons Ltd. Of Manchester, England, presented the Wire Association with this 400-day grandfather clock at its annual convention in Pittsburgh, Pennsylvania on October 20th, 1948. The gesture represented a group of 32 companies from Great Britain. The clock was given in appreciation of the support provided by the U.S. wire industry to Great Britain during World War II. Each year, a representative from the UK makes the trip to the US to participate in the annual ceremony that commemorates the friendship and communication between the two nations. Obviously, this year we're communicating overseas, not present.
Yeah, thank you, Ron. Now it's my great honor to introduce Martin Thacker, our virtual clockwinder for 2020. Mr. Thacker was born in Chesterfield, Derbyshire, and is a freeman of the companies of cultures in his Hallamshire. I hope I pronounced that right. His family's members have had a number of links with the metal and manufacturing industry. His great-grandfather was a cutler manufacturer. His great-grandfather was a wire drawer in Sheffield, and both his father and uncle worked for the Markham and Company Limited. Other family members worked for Brian Duncan, Chesterfield Cylinders, and BERL. Mr. Thacker is also the presiding justice for the Northern Derbyshire Magistrate Bench and vice chair of Northeast Derbyshire District Council. He is a member of the Court of Virtual Footprint Company and Tin Plate Workers, Allies Wire Workers in the City of London. For several years, he has been a panel member for the Metal Industries Apprentices and the year's competition sponsored by the company. Martin?
Thank you, President Jan. Ladies and gentlemen, with the benefit of modern technology, our tradition of clockwinding is able to continue in spite of a worldwide pandemic. As a result, we are creating a new first today. It is a real privilege for me to be invited as the very first clockwinder to participate in this prestigious ceremony without even leaving my home. Although it saddens me that I cannot be with you in person today, we should be glad that the clockwinding is going ahead and the annual tradition remains unbroken. I am mindful that last year, John Drummond, past president of the Wire Foundation, outlined an anniversary linked to the day of the clockwinding by Lindsay Millington. He referred to the 75th anniversary of D-Day and the days that followed. Well, on this day, 80 years ago, the British Royal Navy launched its first ever aircraft carrier strike in history on the Italian fleet. But particularly poignant is that on this day in 1918, an armistice was signed which marked the end of World War I. During that war, my grandfather became an apprentice at Johnson and Playfair wire manufacturers in Sheffield. His wages were 8 shillings a week with a war bonus of a further 2 shillings. The company produced patent and plough steel rope wires as well as high strain steel wire. The advent of the Second World War saw my grandfather move to Brearley and Company as a wire drawer for the princely sum of 80 shillings a week. The company was well known for production of bright wire for all purposes. My grandfather was proud of the work he did and how the wire produced made a difference to the world he lived in. He was equally proud to be an official in the Amalgamated Union of Wire Drawers. The union was the oldest trade union operating in the wire industry, founded in 1840. My grandfather was a union official when there were 13,000 members, and he was invited to attend the Trades Union Congress of 1968. His love of the industry inspired me to become a liveryman of the Worshipful Company of Tin Plate Workers, alias Wire Workers, in the City of London. My proposer for membership was Peter Rigby, a past master of the livery company and clockwinder. And of course, his father was John Rigby, who presented the clock in 1948 on behalf of the British Wire Association. Just like the hands of this clock, the many links ensure we come full circle. According to one definition of a clock, its primary purpose is to display the time. We know that this clock is so much more than that. It is a symbol of so many things, including a friendship between our countries, a practical connection of our wire industries, and the continuation of a bond linked by a metaphor of time-honoured tradition. As the Elizabethan playwright Christopher Marlowe wrote in reference to time, terminat ora diem, terminat aucta opus, which translates as the hour finishes the day, the author finishes his work. So in conclusion, thank you for allowing me to participate in the ceremony today and ensuring that this wonderful tradition is maintained and has meaningful relevance in our 21st century world. Thank you.
Thank you. And now the physical clock winding.
Thank you, Jan. Thank you, Martin. It's a great history lesson there for all of us again. It's always been great to hear that, and it's really great that we continue to do this tradition here at headquarters. So now I guess I'm going to wind the clock. Okay, it's official. It's now been done. Thank you, Martin.
Thank you. I look
can
forward
turn
to
the
doing
crank.
it for real next year.
And next year, hopefully, we can do this in person.
Absolutely. Thank you.
Thank you both for keeping this tradition going on this year here. Appreciated it. As a final part of today's meeting, it's the most anticipated Mordica Lecture entitled Wired Wire Alignment Optimizations Method is given by Dr. Gil Baker. Please submit your questions in the Zoom Q&A panel, and he will fill the question via email after the presentation. Dr. Gil Baker is the principal of Confident Instrument and a US firm that develops custom instrument for QC labs. He holds a PhD and an advanced degrees in medical engineering from Rensselaer Polytechnic Institute and a BS degree in mechanical engineering from Cornell University. He won the WAI's 2011, 2008, and 1993 awards for Best Non-Ference Paper and the 1999 award for Best Journal Paper, as well as a 1998 Essex Technology Award. Gil?
Hi there. Thanks, John. Appreciate it. I'm going to discuss wire die alignment. And again, I want to thank so many people, especially at the Wire Association. Appreciate this honor. It means a lot to me. Of course, I want to say thanks to our veterans today. But worked a lot with Mark Marcelli in the editing, and just recently with Chuck and Janice. And just appreciate this organization. I've been involved with it for about 3 decades now. But anyways, today I want to discuss wire die alignment. And the interesting part is that there's actually 3 categories of wire die alignment. That would surprise a bunch of people because they look at the first category, where I'm going to call it straight wire, or geometry only, meaning only the geometry of the machine dictates the alignment. And typically, in that case, the wire is aligned with the die axis. All right, so again, most people think of alignment as the straight wire. The wire travels straight, so you align it with the die axis coming into the die and align with the die axis exiting the die. This is considered by many as perfect alignment. However, I have 2 other categories to discuss. And this one, in this case, the wire enters the die with a cast or a bow. So it will either enter the die at an angle, or if it's pulled straight by back tension, we still need to put an angle to optimize the alignment. And existing methods of this, of optimizing this alignment, have been used for over 50 years. So it's not something new. We could discuss that. Lining for the finish coiling or straightness is another category where manufacturers purposely put an angle from the exiting wire to the die axis, or they could put an angle from the entering wire to the die axis. And this will control the cast and the helix on the finished wire so that you can spool very nicely onto the spool. That gives it more optimal spooling. It's also used to optimize straightness or to minimize the impact of a straightening device afterwards, because they're useful, but straightening devices also will impact the quality of the wire. I was working on a robotic microphone about 2 decades ago, and I met somebody from the recording industry, which I wasn't familiar with, and he says, he wanted to tell me something. He said, an inch is worth $1,000. And what he means by that is that moving the microphone to the right place, and here you see 3 different microphones, they might switch back and forth or combine them, moving it into the right place to hear the music, even an inch, can be worth $1,000 worth of expensive recording equipment. And I think this is a very good analogy for what we're doing. We're moving the alignment of the die just a little bit, maybe a half a degree, and that is creating an improved condition in the die without increasing the quality of lubricant, the quality of dies, or any other expensive issue. And it's really quite interesting, this analogy, because, for example, I would, if someone told me to put a microphone near a guitar, I'd put it right at the mouth of the guitar. But that's not the way, that's not the optimum. The optimum is further away. And I don't know why. The sound is coming from everywhere, not just the mouth, I assume. But again, when the die alignment is also non-intuitive. And non-intuitive can be good because it means that not everyone knows about it. So, for example, we just break this down with the microphone example. If you purchase new equipment, that's expensive. But just moving the microphone, it's inexpensive, but it requires quite a bit of patience, understanding. You have to get the whole team on board with where you're putting the microphone. The goal in achievement is straightforward. A lot of times you just take new equipment out of the box, plug it in, you're done. But this is very moving the microphone is non-intuitive. Where do you move it to? How do you move it? Further advantages, and so again, this is intuitive, but another advantage is the microphone movement is upstream in the process. It captures the initial sound, and then it's processed later by the expensive equipment, which it still can be expensive. This equipment still can be expensive. Similarly, in die alignment, if you don't have the die aligned properly, it doesn't matter how much expenses you're putting into the lubricant and die, there's still going to be issues that could have been resolved. So let me just go over what we're going to discuss today. I'm not going to get to everything, but again, I'm talking about a different type of alignment than the straight alignment. We won't talk that much about straight alignment, but this alignment is straight. It just depends on the geometry and the equipment. And I'm talking about when there's a strong cast or a bow in the wire, how you have to optimize it in better with a different technique. And I'm going to discuss what processes can especially benefit, touch really lightly on measuring the alignment. Now I'm going to really go into this subject for a while. What I'm discussing here is deconstructing typical wire drawing, because a lot of times we just see wire drawing as a picture of a die, and there's a lot more going on. Existing alignment methods for using this alignment with the strong cast and been in use for over 50 years. There's a number of methods. I put some in my article, but I'm going to touch on two low-cost methods today and assessments for aligning the die. And I'm also going to talk about laser alignment measuring methods. I'm just going to touch on that. Now, again, I'm not going to get to all this other items on the page here, but I am putting things on my website, and I'll put more on later in a few weeks. Now, what processes can especially benefit? Well, number one, hydrodynamic lubrication, of course, is great. It's a great boon to wire drawing unless you go at a higher speed, but it's a very fragile dynamic. The film thickness from the lubricant is fragile. Anything that would disturb it is going to reduce the film thickness and cause more frictional heating and just contact between the wire and the die. So when you just have slight perturbations to the hydrodynamic lubrication, either through this unoptimal alignment or through wire oscillations, you are deteriorating your hydrodynamic lubrication. The wire temperatures are going to increase. And that brings it to the next one. When you want to reach higher drawing speeds, you really need to keep the wire temperature lower, because the wire temperature gets too high, then you cannot draw faster at all. And especially true in steels, where higher temperatures can cause brittleness. And finally, there's where you have a finished straightness needed. Then again, really pay attention to optimizing the alignment for the maximum straightness. And even if you're straightening afterwards, again, you want to minimize the impact of your straightener. Again, where homogeneity is desired, that also is impacted by the alignment. Yoshida has already used some of these concepts in superfine wire drawing. And of course, shape wire drawing is another issue where the homogeneity, the path is so important there. I'm going to go back to these two categories one more time. So you have straight wire, and that is only governed by the geometry of the machine. So you're assuming the wire is traveling straight between the capstans and the spools or whatever. And it's only governed by the geometry. People assume that's the perfect alignment. What I'm discussing mostly here is what I call the wire properties alignment. I say wire properties because when the wire properties change, the alignment must change. A lot of times it will change just a little bit, but if you have to string a new die set that are dramatically different than the other die string, then that causes a big change. For example, in maybe number of wraps, die back tension, things like that. So this type of alignment is important when there is a cast in the wire. And it's really easy to measure whether there is a cast in the wire or not, and how much significance that will play. So we'll get onto that later. So again, this is a picture of straight alignment. The wire is just, you're coming off the spool, going into the die and going onto a bull block. And again, the wire axis and the die axis mate here and here, entering and exiting. Here's another example, but here you have a roll that seems to be adjustable, and that's going to change your alignment. And there's a lot of things that will change even straight alignment. I'm not going to discuss that here, but I just want to make people aware that as we add different complexities, such as cone type and other complexities, we are going also off the straight alignment. Alignment measuring. If you want to measure the alignment, and a lot of times the die holders are already aligned coming from the OEM. So they're fixed, and a lot of times people don't even bother what position they're in. But actually, even some OEMs will put in a different alignment. You might be surprised. So you could check that, but you might be happy with how it's set. A lot of people like to use a laser. There's intricacies with using a laser that we're going to go into later. But they use it because it's used for machine alignment. Another option is a taut flexible string. Now, again, this is only for straight alignment, where the string will be full taut and the string will be straight due to the tension wherever it moves. You could do a similar thing with a insulated stranded wire, where you're stripping half the wire, leaving the insulation on the other. So the change from insulated wire to bare stranded wire gives you a change in diameter similar to wire drawing. Also, perhaps you could use the bare stranded wire as a continuity check between the die and the wire, such that the stranded will bolt straight through the die when it's perfectly aligned. Now there's another way you could use an angle finder with maybe a V groove put into it, and put that directly on this already strung wire that has remained taut or been pulled taut. Again, this is only going to work if the wire is straight when it's taut. And again, you could just use 3D modeling of all the machinery and set up your alignment with the 3D modeling. This is what I'm going to really stress in this presentation: deconstructing typical wire drawing. Again, I mentioned that a lot of times you'll see a picture of wire drawing, you'll see a die with a nice conical wire going through it. But there's a lot of other things going on, maybe in the background, so to speak. So we're going to talk about one where we call this die 1. And so the wire is exiting that die. What's happening there? Then 2, it coils onto a capstan. 3, uncoiling from that same capstan. And 4, entering die 2. We're going to see what that's going to look like. Now, again, this is just a simple illustration, and you might have something that looks different or more complexity. So starting with the first condition, what happens when the wire exits a die? And we're going to forget about reeling off a coil, anything like that. So we're going to assume the wire is perfectly straight, meaning that it would remain straight when draw stress is removed. When I keep talking about straight or cast, if you pull a wire, you pull it, you can make it very straight. but if it has a cast and you release the tension, it'll go. So we're going to assume for now that this wire is coming out straight. The wire has a perfectly round cross section. Again, we're going to assume that the die's bearing is perfectly round and the wire comes out perfectly round. The wire has imposed stress, so this is the stress imposed upon it. That's an important part. And that's the draw stress. The wire will have residual stresses induced upon it when it cools. And for now, we're going to assume those residual stresses are axisymmetric. So axisymmetric is typically how you think of a round wire with a round cross section, axisymmetric. I could just call it symmetric, but we're going to talk about asymmetric later. So there are residual stresses coming out in the wire coming out of the die. Well, the wire comes out without any residual stresses, but there's temperature gradients in the wire. Typically at the speeds we run in production, the surface temperature of the wire is going to be much hotter than the center. So as the wire comes out the die, the surface is going to contract as the temperature equilibrates and as a little cooling at the surface is going to contract. So it's got the tension pulling it. That tension pulling it causes a compression at the center. So now this is what we have in typical manufactured wire. We have residual stresses, and we're again calling this axisymmetric residual stresses. It's symmetric about this line. There are a number of ways of measuring residual stress, and I'm not going to go into that. There's a lot of complex devices, but I want to illustrate what residual stresses are by showing some mechanical means of measuring them. So let's say you had a bar. Similarly, you have tension on the edges of the bar and compression in the center. When a slit is cut in that bar, the bar will separate by a certain measurement here. And that measurement dimension can give you an estimate of the stress in that strip of bar. Similarly, if you're drawing tubing and you slit the tubing, it will also separate by a certain unit of measurement, and that will give you an estimate of the stress. Now, Shida et al. Used similar method. They slit a very fine wire, and I guess they must have used the EDM, wire EDM, both to slit it and cut off that bottom part, unlike here. And again, they're looking at a deflection of this uncut, of the cut part, half the wire. They're looking at the deflection, and then using that deflection plus the length of the slitting and the diameter of the wire, also Poisson's ratio and the elastic modulus. And so they're determining or roughly approximating the residual stresses in the wire. And of course, they use more complex equipment, but this is just a check. But it also, again, looks at what's going on. In fact, you will typically see that when there's high residual stresses, there's going to be a greater occurrence of central bursting and things like that. So the residual stresses are important, and they're important in our understanding of wire drawing. Pardon me just a moment, I'm going to close the window. Okay, so going to the second part of our deconstruction, when the wire comes to the capstan, it coils, and that's not necessarily a simple process. So we're going to look at that. Just give you some illustrations. Let's say you had a device, and this is rigid here, and you had a fixture that's revolving around a mandrel. So it causes the wire to bend 180 degrees. Now, if the wire remains completely elastic in this process, when you release this this fixture here, you're going to have the wire spring back as if nothing had happened. There's no history or memory of what occurred. It's going to look just as straight as it was here. However, if there's yielding, and that's mainly going to be given by this ratio of the wire diameter to the mandrel diameter. And if there's yielding, then there'll be spring back, but not all the way spring back to straight. There will remain a curve in the wire. Again, this curve is like the cast and for the bowl we're talking about. But this is just for a sliding fixture. What if you superimpose tension? And that's what happens in wire joining. You're superimposing tension on both the entering and exiting wire as it goes around a capstan. In that case, there'll be much less spring back because there's more yielding. There's more yielding in tension to create a tighter wind around the mandrel, and so there's less spring back. I just wanted to illustrate that because this is a lot of times this is the problem we're having, where now we have a greater influence upon the wire, less spring back. Now, the next thing we do is uncoiling, number 3. So now we want to uncoil that wire, as I showed you previously, that has the shape in it. Its shape is already set into it. So now we want to uncoil it, but unless there's more devices here, we're typically just doing that with the back tension and the motor revolving of the capstan. So we have to get from being coiled to straightened in some way. And when the back tension is low, you can even see the bow coming off the capstan. I have this flipped a bit, so to show it in the same light here, it would be coming off the capstan here, and then maybe coming straight right before it enters the die. Well, this is a problem because the back tension is not going to fully straighten the wire just by itself, nor with just the movement. In fact, if you look at a typical equation for winding on a mandrel capstan, you will see that the draw stress always has to be higher than the back tension. So you're imposing more stress to shape the wire around the capstan than you are to straighten it back again. So this equation, and you see that if you look at this equation, you have the 2, the pi, the number of reps, that's positive, and the coefficient of friction, typically always positive. So we have draw stress is going to always be higher than back stress, and therefore you just look at it and say, well, you're not going to be able to straighten the wire out unless it's remains elastic. So that is really the problem and why we need a different alignment type. So uncoiling, let's see, if the wire is perfectly elastic, well, then that's fine. But if there is, if there was yielding, both on coiling and uncoiling, it makes the scenario harder that the wire would be straightened just by back tension. And the lower the back tension, the less the straightening. So the ultimate result is there's often a complex asymmetric, now this is not axisymmetric, asymmetric residual stresses in the wire. We mentioned that this is the axisymmetric coming out of die 1. We're assuming it was axisymmetric. But then you had the coiling transformation, that's asymmetric. And you have the uncoiling transformation, also asymmetric. And so you might end up with a shape like this. Again, I just made this up, but I know that there will be compression in the wire here, and I know that there might be a little bit of tension here from the uncoiling. Okay, so now we're entering die 2 with those altered residual stresses, asymmetric, and also slightly different geometry. The wire is not round anymore. It's slightly out of round. Now, again, this is for non-elastic coiling. If it's elastic, I forget what I said. The entering conditions ranges between 2 extremes. So I'm going to just show you 2 of the extremes. The back tension is low. When it's low, it moves the cast state and thus enters the die at an angle. So let's see that. So I kind of combined this where you have this wire coming in with a back tension low. So it's coming in with a cast. You would see the cast because the back tension is so low. You'd see the cast between the capstan and the die. And it's coming in at an angle. There's not really residual stresses because the residual stresses are mostly causing it to curve. And we'll see what happens there. Let me go back to the previous. So it considered no residual stresses, and the wire is forced to enter at an angle to the die axis. Now, the second extreme is the back tension is high enough to pull, to cause the wire to move straight. And even though the wire moves straight, it's not that simple because here in the bottom one here, we're assuming the wire is moving in straight. But because of, for example, compressive residual stresses, again, asymmetric residual stresses, it causes a change in the deformation zone. It's not the neat deformation zone we typically see that's trapezoidal. And you see that this angle is different. Well, here where there's compressive stress, residual stresses, it's harder for the wire to yield. It's harder to get to a yield criterion. So the wire is waiting to yield where the stresses are built up to cause it to yield. Down here where there's maybe some tension or let's say no residual stresses at all, the wire can yield faster. So it changes the shape of the deformation zone. And this causes issues. Like for example, if you have hydrodynamic lubrication, you'll have greater friction and pressure here. In other words, hydrodynamic lubrication creates a film and the pressure between the die and wire are going to dictate the thickness of that film. But here, you're going to have higher pressure. Here you'll have lower pressure, but longer frictional contact. So actually both surfaces can be bad, but this is especially bad for hydrodynamic lubrication. Finally, another interesting thing, and I talk about this more in the article, that asymmetric drawing creates asymmetric wire at the end. And I kind of did touch on that a little bit when I said there was three categories. In the last category, I said where people were purposely changing the angle of the wire entering the die or the wire exiting the die. And when the wire enters the die at an angle asymmetric, there's asymmetry in the exiting wire. It's not like the wire we discussed at die 1 where it's round. I mean it's round, but where it has no asymmetric residual stresses. So what's going to happen is, for example, it'll be hotter. The surface temperature will get hotter. Again, especially with the hydrodynamic lubrication. And so that's going to cool down further and create greater tension here than here where the wire surface was cooler. But the second thing is that when a particle of metal goes through this part of the deformation zone, you're going to have more strain hardening. So for micro hardness, you will have a harder material up here than you do down here. So two things that make the wire exiting asymmetric. And here's some examples of wires that are asymmetric in their deformation zone. Here's a SEM picture, and we put on two values we use to measure the asymmetry that's in the article. Here, let me just say these were drawn in a high-speed bull block at Polytechnic Institute under Roger Wright. And here's an image on the optical microscope. So I recommend backlighting in the optical microscope because it's harder to see than in the SEM. But again, we use this S and the L, S for short and the L for the long. Here's some examples from an article written by Austin on superconductor wire. And he was having problems with wire breaks, and he believes that the asymmetry in the deformation zone here and shown here caused those breaks. Again, drawing superconductor wire, just you're very concerned about the shape of the internal product. So there's another reason you always want to improve your die alignment there. Now, a lot of people are asking, well, what factors cause cast? Again, I said, and I'm going to remark down here, it's very easy to measure cast. So that's probably the first thing you should do. But what parameters do influence it? People want to know, they want to see, well, what processes are going to have more cast? And the main parameter is the wire to capstan diameter ratio. Again, I kind of showed that with the wire on the mandrel. So if a little wire is on a big mandrel, it might stay elastic. But if a big wire is on a small mandrel, then you're going to have more yielding. And that's especially the case of cone type wire, cone type drawing, because then the wire comes in at the largest diameter on the smallest capstan, and the cones go up from there. So what I showed you before is that we have the coiling and also the uncoiling. So for coiling, the wire diameter ratio is important and the elastic modulus. And as the wire diameter ratio increases, wire to capstan diameter ratio increases, there's going to be more cast. As the elastic modulus increases, that's a bigger influence towards cast in the coiling. And I have some examples of E modulus. Now for elastic modulus related to uncoiling, it's kind of the reverse, because now you want to straighten the wire back again. And so having a lower E is worse, or having a higher E was going to help. Back tension, of course, I mentioned before that back tension is really straightening your wire back again. So how high that is going to be important. You're going to have more cast when you have a lower back tension. Previous gross stress to flow stress ratio. And again, the back tension has to cause, or this is for coiling, the flow stress, the draw stress is going to cause yielding in the wire. And similarly, when you are uncoiling, the somewhere here, the flow stress and the tensile, the back stress and the, oh, that's up here. Okay, so these two are up here. Now there's also the issue of residual stresses. Even if they're axisymmetric, the tension from the residual stresses on the surface of the wire, near the surface of the wire, is going to cause issues in your coiling, or is going to influence your coiling and your uncoiling. Actually, it's going to be worse. So the cast is going to be higher with more tensile residual stress, even if they are axisymmetric. Again, again, they could be asymmetric from previous dies, as I showed before. The wire cooling on the capstan, that's going to have an influence. Now, I've kind of gone down here. There's lesser and lesser influence as we go down. But I'm just listing everything. But again, the main thing is just to get out and measure the cast. And that's most important, probably because someone can make a model. So I mentioned here on this first slide, the main issue is wire to capstan diameter ratio. But it doesn't mean you could just make your capstans as high as you want, because there's a cost to restringing the dies. It takes longer with a larger capstan, and the machine will be bigger. But let's just take that issue. Here, imagine a wire going, and this one has a large capstan. So the wire to capstan diameter ratio is going to be low here. And then let's take another example of a wire, and that's pulled through on a capstan, and that capstan is maybe about half the size in diameter. So here you have a high wire to capstan diameter ratio. So we come through here. This wire starts out straight. This wire, we can assume, also starts out straight. After just the coiling and uncoiling, we have a wire with very little cast, low wire to capstan diameter ratio. However, when you have the higher wire to capstan diameter ratio, after it comes off coiling, you're going to have a cast in your wire. And this is showing the cast with no tension, meaning the back tension might show the wire straight into the die, but in fact, if you took off the tension, this wire would have a cast to it, or a bowing to it, or a camber. Now, let's say they both go into this die. This one goes in straight, and there's very little asymmetric residual stresses. There are still residual stresses, but because it's symmetric, the wire is symmetric, the deformation zone ends up being symmetric. And this, in turn, the wire comes out symmetric, like this yellow wire here as an example, with no tension. Now, going into the same die where you have your cast, you have your bowing. So that means even though the wire is straight going into the die, there are residual stresses, asymmetric residual stresses, that is, and they cause a different deformation zone. The deformation zone is asymmetric. Again, there's compression here. It takes longer for the material here to yield, and the wire prefers it decides for itself. I'm going to shift to a more favorable position. And so that comes out also with a bow. As I mentioned before, asymmetric drawing begets asymmetric wires. Okay. Now, there are existing alignment methods of this method where you're considering the cast, and you're considering it as a steady state issue, not something you can just measure in the machine geometry. And most of those methods in the past, and for about 50 years, have used the die wear, analyzing the die wear to determine how to optimize alignment, with the goal being of maintaining as axisymmetric or symmetric a die wear as possible. So this involves examining the dies. Now, the one method is just looking at worn dies. Maybe you've used the dies long enough, you want to replace them. just look at the worn dies. Now, whether or not you have had those dies prevented from rotating through their service life, that's you'd have to ask someone else like that about that. But you definitely want to look at those dies coming out of service. Now, the second way this is used is you can string in a set of dies that are rapidly wearing dies. So, for example, most people are using various types of diamond dies nowadays. So if you put in a tungsten carbide die, it will wear much faster. Or if you have maybe a soft metal, you might even use tool steel to get a rapid wearing die. Now, again, I would say you want to prevent the die rotation, and this would be just drawing over a few hours. And after those hours of drawing, you want to examine the die, and you will see if the die, if there's a symmetric deformation zone. Now, again, with cast, there'll never be a symmetric deformation zone, but you can adjust the alignment such that you can improve the deformation zone. In the article, we go into a high-speed alignment optimizing experiment. And in that experiment, we determined that we wanted 2 degrees off the die axis in the upward. In other words, here's the capstan and the wire is coming in a little bit upward. And again, I'm not going to go through all this, that's in the article. So the methods of measuring cast, I'm just going to touch on 2 simple and low-cost ones. And you can either create a break in the wire while the machine is running by running the wire through like a jaw that's going to clamp pretty quickly, pneumatically, for example. Or you could go in and do your analysis when there's a natural wire break. And in those cases, you're preserving the what's going on in the deformation zone downstream of the breaks. So you preserve that, and now we can look and see what the deformation zone looks like before you have to pull the wire out of the die. Of course, I would mark everything relative to the die so you're able to orient yourself. And then here's an example of a wire with the mark where it was relative to the die. And what you're going to do is look at and measure that S and the L, like L being the longest length in the deformation zone and S being the shortest length. I put it in a collet because it's really an exact measurement, especially if the cast is not in the same plane as the 12 o'clock of the die. So that's also discussed in the article. So here again is the S and the L, and there's I should have probably put it here, but there's an equation in the article. The next way is to measure cast itself. And I'm not sure if this is easier or harder, but you have been drawing wire through some dies, and perhaps there was a break. Now, you need to loosen up, so maybe pull some more wire from this die to loosen the wire here so that it's not, there's no back tension imposed upon it. So this whole wire is loose now. So you need some kind of clamp to hold that wire to the capstan where the wire was exiting the capstan. So here, maybe at the 12 o'clock part, but it could have been exiting another part. So here, that's the first thing you do is put kind of a clamp or a press to hold that there. You're going to know the length, and you can make this measurement. You can create a line here with a laser, or you can, create use a stiff rod or something to create a line, and then measure this. And this can be done with a photograph adjusted probably with a scale to make sure you have it at the right angle. So now you measure the height, and then you can determine the cast, which the cast is really this. When people refer to cast, they're really referring to this radius, the radius of curvature, curvature being the inverse of that radius. So with the H, which is here, I put it in capital, but it's really the small h, and the L, you will be able to determine the radius. So you don't have to actually measure the radius. You determine that. So I mentioned two low-cost methods of measuring the issues in alignment. I think that measuring the deformation zone itself and measuring the cast itself are more immediate and more direct than measuring die wear or anything else. There's some more complex load cells and things like that, like we did with the high-speed experiment. But that is a low-cost method. They take time. And also there are low-cost methods where you don't have adjustable die holders. Many people don't have adjustable die holders. So there are low-cost methods there, and I mentioned them in the article, and probably I'll put them in the website later. Also, you don't have to align the die every week or every day, but you would if you're changing die strings dramatically, things like that. But if you wanted to measure alignment and adjust alignment annually, then again, you could do that when you have some downtime. It's really not a high cost method of improving the drawing process. So finally, I'd like to, I mentioned before about methods of checking the alignment. And a lot of people like to use lasers. I'm not sure if that's the best thing. There are some issues with using a laser. Of course, eye safety, depending on the laser, of course, that's one important thing. But, people use lasers. They see it on the CSI, or of course, fancy machines are aligned with lasers. The issues, first of all, and we've actually developed a product to make it compact. A lot of the other systems are too big, and also easy to adjust. You think it's going to be easy to adjust a laser, but it's not like putting a physical rod into a wire or into a die, or a string or anything into a die. You don't have that physical constraint to help you. So what we have designed is something that has a coarse measurement that can be done manually in 3 degrees of freedom, and then motorized or galvanometer methods to move the laser slightly at fine pace so that you can get that precise touch. You don't want the laser to touch the capstan, go directly through the die and touch the other capstan. And again, what size of beam you use is important, because if your beam is too big, it's not accurate, but also there could be issues, especially if you take a natural diamond die, you might have some refraction here. This thing called diffraction, even with all dies. So we might want to use a laser that will fit through the die and is considered aligned when it's not touching the die at all. And so the bad thing about that is those lasers with the very fine beam are hard to see. So, you can spray your water, but you're going to have trouble seeing them. So we're designing where you could flip in a laser you can see with a bigger beam, and a laser with a finer beam for more accuracy. And by the way, the finer beam laser would be more dangerous for the eyesight. So that's important. Now, here's the references, and I think these slides will be available. I'm making them available, and I will continue to update the website as well. So thanks for listening. I didn't want to go too long, but if you well, mostly I think for such a complex discussion, I'm looking to take questions with the email, but I will turn it back over to Jan and see what he would like to do.
Thank you very much, Gil, for this informative information. This concludes our today's meeting, and the WAI upcoming WA's upcoming events will be posted online and in the Monty Wire journal. Thank you for everybody for their participation, and also a special thanks to all the people at WAI for working behind the screen. And thank you again for joining us and bringing the distance to stay close in the stream. Stay safe and stay well out there. Thanks for being here today. Goodbye.